Our next speaker is Henrik Kofoed-Hansen, who's Vice President of Marine Water for the DHI Group. Henrik has more than 25 years of professional experience in the field of offshore port and coastal engineering, with emphasis on metocean processes and data, water structure ship interactions, and advanced numerical and physical modeling. After almost 9 years leadership of DHI's Ports and Offshore Technology Department, Henrik is today responsible for the strategic development and growth of the marine water business sector within the DHI Group's more than 30 offices across the globe. And Henrik, today, his subject is going to be adapting to climate change, value modeling tools for sustainable solutions. Henrik.
Thank you, Kevin. It's not a bad excuse. I also have a bad voice, as Adam. I will do my best. And I will also promise you one thing. There's a small exercise during my slide here, so don't fall asleep, okay? I will start with a short introduction of DHI, a little bit on the principle we have been working along for quite some time, 2 interesting case stories, and what's next. Started with a port more than 50 years ago. DHI was asked to build a harbor in a location with a very harsh environment. Tough waves and a tough sediment climate. A lot of sediment is passing this part of the North Sea. We did a physical model of that, as you can see to the left here, to convince policymakers that this is doable. And it was built. And guess what? Now it's going to be extended again. This was the start of DHI. Today we are a not-for-profit, independent, research-based organization. 1,100 people across the world. Research and development is our nature. It's very important to innovate the business. And we try to make this knowledge accessible for you guys. We have experience for 100 projects in 150 countries around the world. So we are indeed a very global company. And our quest is to help solving the world's toughest challenges in water environments, in the changing water environments nowadays. So water is our world. Models. This is very much about models, following the first presentation. As I said before, DHI was established on physical models, but at a very early stage, some visionary people said that doing physical models is very expensive. We have to do a more smart way. And that was this guy here, Mike Abbott, who started as one of the pioneering in developing numerical models. That has been the starting point for the success of DHI making software for the modeling communities, where I know quite a few people here inside this room are using these models for many years. At the same time, it's also important to emphasize working with nature has always been the principle for DHI in what we are doing in water environments, to improve resilience and to adapt to climate change. That requires a very deep understanding of the natural processes, a lot of math, numerical modeling, but also creativity and innovation. Models play a very important role today to find these solutions. With boundary conditions which are changing, we don't know the boundary conditions. So this is what we call the known unknown. But we have to come up with solutions. I will take you back to Denmark. Limfjord is 180-kilometer fjord connecting the North Sea to the inner Danish water. 150 years ago, it was closed here. But then a major storm from the North Sea came and breached the dike there. And since then, it has been open. It's no secret that a number of the port cities around this Limfjord is having increasing flooding issues, especially this part here. And then one of the questions was, is that due to sea level changes, or it's due to other features? This is actually the entrance to the inlet, and you can see a very rapid development of the morphology. And if you look over the years, over the past 50 years, it's easy to see how big changes you have in this inlet. And if you look at the cross-sectional area here, this is the area versus time, you can see it's more and more water is coming in, which is one of the reasons why we have increased flooding in this area. Here you can see this town we are looking at. So what to do to quantify this? I mean, first of all, you set up a hydrodynamic model and sediment transport model to study the quantification of the morphological changes. And here you can see a couple of examples, snapshot of what we call high-resolution models, which are validated compared to measurements. And fortunately, we have many measurements in this area, so we can make a very robust model. Then we can run a number of scenarios. We can run historical storms. We can run scenarios in the future. But let's start with some of the historical storms and make the analysis. If you consider the condition as it is today, then you have a water level versus return period here. This is the present situation. But if you extrapolate the morphological evolution into the future and do the same calculation with a number of historical storms, you see a picture like this one. And for the 100-year event, we see an increase of 40 centimeter in water level. Nothing to do with climate change, but due to morphological evolution. With our models, it has been impossible to assess. When you have the models, you can also test a number of options, how to mitigate this, how to adapt it. And here you can see a number of examples. You can extend existing groins. You can calculate the cost of it and the other implications. As I just said, that morphological evolution is responsible for 40 centimeter increase. So we have to narrow it down to 300 meter like a solution like this one to get equilibrium. This is a solution that costs around 50 million euro. Alternative is, of course, making a barrier, which is probably 10 times more expensive. Presently, a local solution was implemented in this city. They built a dike here in a smart way, and it works. As you can see on this picture, this is the port during a major storm. So that was a local solution embedded here. Now the exercise is coming. Are you ready? We're back to the port here. A few years ago, there was no major issue with waves and overtopping waves. But then we saw this one. And this picture is actually taken here. The waves are running over here, quite violent, during a reasonable calm day. Now the climate changes are coming. What is it? It was very unusual. I have never seen something like that. It caused a lot of disturbance inside the ports and, of course, damage on the structure itself. But what is the next step? What to look after to investigate this? What is the first thing you will do? Look at the bathymetry, right? We look at the previous survey, probably a 1 month or 2 month old. or even older, and the new one. Subtract these two from each other. When I asked quite a few people, they said there are no difference. Yes, there are. There are differences. But then you can use a model, one of the wave models. This is the area. That was the previous situation, that's a new situation. You can see much higher waves here than here. What's the reason? This one. The sandbar, small sandbar, causing a lot of troubles. Solution is easy. Remove it, and they did. Cheap solution, understand the nature, and do applicable models. That's the lesson learned here. What's next? One thing is that you can do a lot of modeling, and the pain is really real, as we discussed. We have a known unknown. The details are not clear yet. It's very uncertain. But the trend is it's going to get worse. So we have to take some actions to reduce the losses we see. Otherwise, it results in bigger losses in the future. And that calls what we call for decision support systems that can help in our planning and prioritization. What kind of interventions are needed? When are they needed? And where? What are the optimal solutions? Looking at a number of different criteria, and how much does it cost? This is a framework we have been working on. I mean, there are many organizations worldwide working on the same framework, but we had the aim of developing a tool that could support the industry, basically split into 3 different areas. I mean, the first one is understanding the problem, making the hazard models, the water models, then the financial models. I mean, what are the costs, direct and indirect cost, and to study these cases here. And of course, the output is risk assessment for existing situations. But on top of that, also evaluate different kind of intervention options. And eventually, that will help take the right decisions, we believe. So our vision, working on this tool, is to offering a unique and easy-to-use GIS tool, combining water domain knowledge and RE-driven decision-making. The latter one is a new one from a water modeling company like DHI. Therefore, we have invited a number of partners to work together with us on this. We believe this kind of tools will enable policy and decision makers to make these informed decisions in the context of a situation where we have unclear boundary conditions. And this is my end slide here. It's always a good idea to start with say, what is the worst case envelope in a do-nothing scenario? What will happen? To set the scene. But then, as Adam also said, that it's quite important that we are simply not going crazy with a number of different models, but use the right tools and the right data during the process. I think that's it. Thank you.